I am Dr.S.Prasanna, Assistant Professor of Mathematics in Pingil Government College for Women. Yesterday, we have gone through the topic vector spaces and we have learned what is the definition of vector space, and we have seen some examples of vector space. Let us see what is vector space once again before going to the properties of vector space, which is the today's topic. And the vector space is nothing but a set of vectors, and usually it is denoted by capital V, and we need a set of scalars to define a vector space, and that usually we take as the set of real numbers R, and the vector space usually is denoted as V over R, or simply V itself, as R is fixed. Many times we take the set of real numbers as the set of scalars, so we need not represent R every time. So we take simply V for the notation of a vector space. And this set of vectors V over the set of scalars R is said to be a vector space under the two operations. And what are they? They are addition and scalar multiplication. And that addition is actually particularly vector addition, and another operation is scalar multiplication. And those are defined on V in such a way that the elements of V over R satisfy 10 axioms, and out of the 10 axioms, 5 axioms are under addition operation, and 3 axioms are under scalar multiplication operation, and the remaining 2 are under distributive laws properties. And what are the axioms that come under addition? There are 5 axioms, and what are they? The first one says that V is closed, V has to be closed under operation addition. For that, we have to show that U bar plus V bar is in V whenever U bar and V bar are any two vectors in V. That means sum of two vectors in V is again an element in V. So that is how V will be closed under the operation addition. And the second property says that the associative axiom with respect to addition. And here we can see U bar plus V bar plus W bar is equal to U bar plus V bar plus W bar. That is the associative axiom condition. And the third one is regarding identity axiom, about the identity existence of identity element, and we can see the zero vector 0 bar consisting of all elements as zeros that exists in V obviously, and that can be regarded as the identity with respect to addition, additive identity in the set V over this set R. And the next one is inverse axiom. For every element U bar in V, we can see that the negative of U bar, which is denoted by minus U bar, exists in V in such a way that U bar plus minus U bar is equal to 0 bar. And by this we can say that minus U bar is the additive inverse of U bar in V. That means inverse axiom this defines the inverse axiom in the set V over R. Next, the last property with respect to addition is commutative axiom, and that states that U bar plus V bar is equal to V bar plus U bar. And the next axioms, 3 axioms are under scalar multiplication, and the sixth property is itself the definition of scalar multiplication in the set V. And what does it state? See, there is a scalar, I have taken a scalar C and a vector U bar, and if CU bar, if the product CU bar, that means the scalar multiple of the vector u bar. If that belongs to the set V again, that means that is also u bar is also a vector in V, and then we say that scalar multiplication exists in V. And the 7th and 8th axioms are also pertaining to the operation scalar multiplication in V, and they state that 1 dot u bar is equal to u bar, and c times of d u bar is equal to c d times u bar, where c comma d are scalars and u bar is a vector in V. And the last two axioms are distributive axioms, and these distributive axioms at a time consists of both addition and scalar multiplication, and there are two axioms. First one states that c times of u bar plus v bar is equal to c u bar plus c v bar. That means scalar multiplication of addition of vectors is equal to addition of scalar multiples of u bar and v bar by the scalar c. And the last one says that c plus d of u bar is equal to c u bar plus d u bar. And this is if all these 10 axioms are satisfied in a set, non-empty set V over a set of scalars R, then we say that V over R is a vector space. And the important axioms that are defined within the vector space are: the first axiom, which says that V is closed under addition, and the sixth property, which states that V is closed under scalar multiplication. And next we have seen some examples of vector space already in the previous class. So now I move on to the properties of vector spaces, and these are properties of vector spaces. We are going to prove them, so that is the reason I have taken each property as a theorem, as we are going to prove each property and get the proof of each property. That is why I have taken each property as a theorem statement, and let us go through one by one and see the proofs of those statements too. Now, the first property of vector spaces states that in a vector space V, the 0 vector 0 bar is unique. A vector space V cannot have more than one 0 vectors, and only one element, that is denoted by 0 bar, acts as 0 vector in the vector space V. That is the meaning of this theorem. That means 0 vector which we denote as 0 bar is unique, one and only one vector in the vector space V. So how we can prove that? So usually when we have to prove that a vector or something is unique, then the model we follow is we take any two elements apart from the one we are claiming to be the 0 vector or something unique which is unique. We take another one also, and with the same property, satisfying the same property, and prove that this is a contradiction, or otherwise they both are same. The the element which satisfies the axiom and the we are proposing to be the element which satisfy the same axiom. If both are same, then we can say that the element which satisfies that particular property is unique. So that tactic we use here to prove this theorem, and how it goes, let us see. It is already given in the statement that V is a vector space, and 0 bar is 0 vector in V. So V is a vector space and 0 bar is 0 vector in V, 0 vector. So that is the 0 vector means it is acting as additive identity in the vector space V. What is the function of additive identity? It whenever that additive identity is added to some element, then we get the same element as the resultant vector. So U bar 0 bar is 0 vector in V. That means when we take U bar some vector of V, any vector of V, then U bar plus 0 bar will be equal to U bar. And this holds good for every vector of V. That is why I have taken here U bar 0 bar is 0 vector in V implies U bar plus 0 bar is equal to U bar for all U bar belongs to V. And I have denoted this statement as equation number 1. Let E bar be another 0 vector in V. As I said, we take some other element of V which acts same as that 0 bar, and our claim is that 0 bar and E bar are one and the same, so that 0 bar will be unique in the vector space V. So I am taking another vector which acts just like that 0 vector 0 bar in V. So I have represented it as E bar. So I have taken it as let E bar be the another 0 vector in V, another 0 vector in V. And E bar is not 0 bar, it is something else I have taken apart from 0 bar. Now as 0 bar is an element of V, in place of U bar, take this 0 bar. Now we can say that by equation 1, 0 bar plus E bar is equal to 0 bar. I am applying equation 1. In place of U bar, I am taking the element 0 bar. As 0 bar is also an element of V, and by the equation 1, every element should satisfy that statement, which is that statement U bar plus 0 bar is equal to U bar. In place of U bar, we can take any element of V. So now I am taking that as 0 vector. That means in place of U bar, I am taking 0 bar. And in the just above statement, I have taken that E bar is another 0 vector in V. If E bar is 0 vector in V, then for the element 0 vector of V, 0 bar plus E bar should be equal to 0 bar again, because here E bar is acting as 0 element in V and 0 bar is acting as some arbitrary element of V. So some element of V. So 0 bar plus E bar will be equal to 0 bar, where E bar is the additive identity, as is E bar is the 0 vector in V. If it is so, then let us take this as equation number 2. Then 0 bar plus E bar, but we can say that 0 bar plus E bar is equal to E bar, as 0 bar is 0 vector of V. By the statement 1, equation 1 again, as 0 bar is 0 vector in V, if some 0 bar is added to some element of V, then we should get that element as the resultant. So 0 bar plus E bar should give rise to E bar again, because 0 here I am considering 0 bar as 0 vector of V. So from these two statements we can understand from 2 and this equation 3. The above one I have taken as equation number 2, and now this one I am taking as equation number 3. Then now I can claim from 2 and 3 E bar is equal to 0 bar. This is the conclusion we can draw from equations 2 and 3. And on the whole, what we have proved is that if e bar is some other zero vector in V, then it is nothing but it is equal to 0 bar itself. That means the zero vector 0 bar in the vector space V is unique. One and only one zero vector lies in a vector space. So that is the first property of vector spaces. Now move on to the next property of vector spaces. I have taken that also as a theorem, and what does it state? If it is in a vector space V, if u bar belongs to V, if in a vector space V, if u bar is an element of V, then the negative u minus u bar is unique in V. Then the negative of u bar denoted by minus u bar is in V, is again an element of the vector space V itself. And further it is the theorem states that negative of the given vector is unique in V. It is one and only one negative exists for each vector of the vector space V. So how we can prove this? Given V is a vector space, and it is already given in the statement that the set V is a vector space, and if u bar belongs to V, that means that is also given in the statement itself. So if u bar belongs to V, then there exists minus u bar in V such that u bar plus minus u bar is equal to 0 bar, where 0 bar is zero vector in the vector space V, and this happens by the inverse axiom, which is the fourth axiom in the definition of vector space. And in the definition of vector space, by the fourth axiom, we can understand that every element in the vector space V has some inverse element which is called additive inverse, and that satisfies the property that u bar plus minus u bar is equal to 0 bar. Adding the element and its inverse, we should get the zero vector of that vector space. So u bar plus minus u bar is equal to 0 bar. Now let us take, our aim is to prove that minus u bar is unique, and as in the previous theorem, in this theorem also we use the same technique, that we will take some other element which satisfies which can be replaced by minus u bar. That means there exists some other element in the vector space V which satisfies the equation 1. So I am taking it as w bar. So namely w bar, there exists another vector in this set V, and how is it? Means it satisfies the equation 1 by replacing minus u bar. So let w bar belongs to V such that u bar plus w bar is equal to 0 bar. So adding w bar is also some element which acts as some element of V which acts as additive inverse in V. So u bar plus w bar is equal to 0 bar, and by equation 1 we have u bar plus minus u bar is equal to 0 bar. And now for u bar plus w bar is equal to 0 bar, I am making some operation here. What is it? Means minus u bar, I am taking minus u bar and adding on both sides of u bar plus w bar is equal to 0 bar. And how will it be? The statement now becomes minus u bar plus w bar is equal to minus u bar plus 0 bar, and this implies minus u bar plus w bar is equal to minus u bar plus 0 bar. And what I have done here is, on the left hand side I have used the second property of the vector space definition, which is called associative axiom. So here I have changed the brackets like this using the associative axiom. Then in the brackets we have minus u bar plus u bar, and that is equal to 0 bar by the equation 1. So 0 bar plus w bar is equal to minus u bar plus 0 bar. And on both sides, where 0 bar acts as additive identity, and so that 0 bar plus w bar becomes w bar itself, and on the right hand side minus u bar plus 0 bar becomes minus u bar. So finally what did we get? W bar is equal to minus u bar. That means my w bar is not something else than u bar, but it is the same vector as u bar. So if u bar belongs to V, then the negative minus u bar is unique in the vector space V. Hence the theorem is proved. Hence the property is proved in this way. And let us move on to the third property of the vector space, and it states that if V is a vector space, then 0 u bar is equal to 0 bar for every u bar belongs to V. In the definition of vector space, we have seen that by the property 7, that is seventh axiom. By seventh axiom, 1 dot u bar is equal to u bar. But here it is stating that 0 u bar is equal to 0 bar for every u bar belongs to V. So already in the statement itself, V is mentioned as a vector space. So given V is a vector space, and then 0 u bar is equal to 0 bar is also given to us in the statement itself. I am considering it 0 u bar is equal to 0 bar, and I am writing it as 0 u bar is equal to 0 plus 0 times. I am considering 0 u bar only here, and 0 u bar I am writing it as 0 plus 0 times u bar. From the statement of the theorem, I am taking only the left hand side, which is 0 u bar, and 0 u bar I am rewriting it as 0 plus 0 times u bar, and as 0 plus 0 is anyhow 0 itself, by as 0, the element 0 belongs to the set of real numbers, which is a scalar. Here the 0 is not vector. On left hand side of the statement, the 0 is a scalar. On the right hand side, it is a vector, 0 vector. So now 0 u bar is equal to 0 plus 0 into u bar can be written as 0 u bar plus 0 u bar by the distributive axiom of the definition of vector space. By the distributive axiom, that is the 10th axiom, C plus D times u bar can be written as Cu bar plus Du bar. That property we are applying here and writing it as 0 u bar is equal to 0 u bar plus 0 u bar. Now at this stage, add minus 0 u bar on both sides. Then we get minus 0 u bar plus 0 u bar is equal to minus 0 u bar plus 0 u bar plus 0 u bar. And on the left hand side, minus 0 u bar plus 0 u bar is nothing but 0 bar, because the minus 0 u bar, the element minus 0 u bar is acting as an additive inverse of 0 u bar, and hence we should get the resultant 0 vector. That is how minus 0 u bar plus 0 u bar we have replaced by 0 bar, and on the right hand side also we get 0 bar plus 0 u bar, and 0 bar will be equal to the right hand side we can write it as 0 u bar, because 0 bar acts as additive identity here. And finally we got 0 u bar is equal to 0 bar for every, and this is true for every u bar in the vector space V. So this is how this theorem or this property of the vector space is proved. Now move on to the next theorem or the next property of the vector space, and which states that in a vector space V, C0 bar is equal to 0 bar for every scalar C. So in a vector space V, C0 bar is equal to 0 bar for every scalar C. That means if the 0 vector 0 bar is multiplied by a scalar C, then the resultant vector is the 0 vector itself. So that is what we have to prove here. So for this proof, we are already given in the statement of the theorem that V is a vector space. So I have taken the first line of the proof as given V is a vector space. Then I have taken the left hand side of that part which we have to prove. Only the left hand side we have to take, and that is C0 bar, and we have written it as C times 0 bar plus 0 bar, as 0 bar plus 0 bar is 0 bar again. So this can be further written as C0 bar is equal to C0 bar plus C0 bar. On the right hand side we are applying the ninth property or ninth axiom of definition of vector space, which is called a distributive axiom. So the C0 bar is equal to C0 bar plus C0 bar is the statement we have arrived at. Now at this stage add negative of C0 bar, which is minus C0 bar on both sides of this line, this statement. Then we get minus C0 bar plus C0 bar is equal to minus C0 bar plus C0 bar plus C0 bar, and this is further equal to 0 bar is equal to, this implies 0 bar is equal to 0 bar plus C0 bar. Here what we have done means we have replaced minus C0 bar plus C0 bar by 0 bar. With this we could do by the inverse axiom, which is the fourth property in the definition of vector space. Then we can write it as 0 bar is equal to C0 bar. On the right hand side we have replaced 0 bar plus C0 bar by C0 bar. This can be done by using the additive identity property, which is satisfied by the 0 which is satisfied by the 0 vector 0 bar. Therefore C0 bar is equal to 0 bar for every scalar C. This is how we could prove this property also. Then the last property of the vector spaces states that in a vector space V, if u bar belongs to V, then minus 1 times u bar is equal to minus u bar. And if we move on to the proof, we are already given that V is a vector space, and let us take u bar belongs to V. U bar is a vector in V. Consider u bar plus minus 1 times u bar, and this I am replacing the first vector u bar by 1 dot u bar by the seventh property, which is the second property in the axioms of scalar multiplication. On the whole, in the definition of vector space, it is the seventh property, wherein we have u bar is equal to 1 dot u bar, or 1 dot u bar is equal to u bar. That I am using here and replacing u bar by 1 dot u bar, and we are getting in this way: u bar plus minus 1 times u bar is equal to 1 dot u bar plus minus 1 times u bar, and I am taking u bar common, and this taking the like this u bar common comes under the axiom, distributive axiom, which is the 10th axiom. C plus d times u bar is equal to cu bar plus du bar. Here I am using that property in the reverse manner, that is I am replacing cu bar plus du bar by c plus d times u bar. Here c is 1, d is minus 1. Now the terms which are in the square brackets, 1 plus minus 1 is nothing but it is equal to 0. So on the whole we will get 0 u bar on the right hand side. That means u bar plus minus 1 times u bar is equal to 0 u bar. In the earlier theorem we have proved that it is 0 bar, and that is how u bar plus minus 1 times u bar is equal to 0 bar. That means minus u bar, the negative of u bar, that is minus u bar. If we take that minus u bar and add on both sides of the above statement, we will get minus u bar plus minus 1 times u bar, and that is equal to minus u bar plus 0 bar. On the left hand side, minus u bar plus u bar will be equal to 0 bar because by the inverse axiom, the fourth axiom of vector space definition, and plus minus 1 u bar is equal to minus u bar plus 0 bar is the remaining part of that statement. And now 0 bar plus minus 1 times u bar is nothing but equal to minus 1 times u bar, because 0 bar is the zero vector, 0 is the zero vector which acts as additive identity in the vector space V. So finally we got minus 1 times u bar is equal to minus u bar, because 0 bar plus something is that element itself by the identity axiom, which is the third property of the vector space definition. So this is how we could prove this property also. Now, so if we want to go through the properties of vector spaces once again, so the first property states that in a vector space V, the zero vector 0 bar is unique, and the next property states that in a vector space V, if u bar belongs to V, then the negative minus u bar is unique in V. And the next property states that if V is a vector space, then 0 u bar is equal to 0 bar for every u bar belongs to V. That means 0 u bar, 0 is a scalar here, and 0 bar is the zero vector in V. And if we take 0 u bar, we are going to get the zero vector as the resultant. In the next property, we have seen that C0 bar is equal to 0 bar for every scalar C in a vector space V. And the last property states that in a vector space V, if u bar belongs to V, then minus 1 times u bar is equal to minus u bar. So these are the properties of the vector space. Now we can move on to the problems. So let us prove one problem. It states that show that the set capital H of all points of R2 of the form 3s comma 2 plus 5s is not a vector space by showing that it is not closed under scalar multiplication. Actually, I don't want to give the solution of this problem now itself. You note down the problem I am reading. Show that the set H of all points of R2 of the form 3s comma 2 plus 5s is not a vector space, and this I have given the hint by showing that it is not closed under scalar multiplication. You take down this as an exercise and try to do it. Try to do and get the solution. If you won't get, we will get the solution tomorrow in the next class. And I am giving you another problem also. Write down, let capital H be the set of points inside and on the unit circle in xy plane. That is, let capital H is equal to set of the ordered pairs x comma y such that x square plus y square is less than or equal to 1. That is, H is a subset of the set R2. H consists of all the ordered pairs such that x square plus y square is less than or equal to 1, and this is also in the xy plane. And what is the required to find is, find the specific examples of two vectors and a scalar. Find two specific examples, particularly that means not by taking x comma y, don't take variables but take some numbers. Specific means particularly you have to tell what could be the value of x and what could be the value of y, and show that specific examples two vectors and a scalar also. Find some scalar also to show that H is not a vector space, and your aim should be is to prove that H is not a vector space if H is defined as this set of x comma y such that x square plus y square is less than or equal to 1. Try these two problems as an exercise, and if you won't get, we will do it in the next class. And the next class will be on the taking some problems like this and get the solutions in the next class. So then the next class will be on problems on vector spaces and how we can get the solutions for the given problems. We will see in the next class. You try these two problems and we'll meet in the next class. Okay, children. I have in the previous classes I have gone through some prerequisites topics to learn linear algebra, and in the last class we have started to learn the topic linear algebra, and we have started with the topic vector spaces, and I hope you are following the subject properly and taking now notes or practicing it well, and going through the subject well. I hope so. Okay, children, I remain here.